Up next, we are honored to welcome Professor Nigel Smart from KU Leuven and Zama. Nigel is one of the world's leading cryptographers, a pioneer in homomorphic encryption and secure computation, with a deep commitment to bridging academic research and practical deployment. In his keynote talk, he'll share how advances in cryptography are transforming the way we compute and collaborate securely. Please welcome Professor Nigel Smart.
Hold on. Oh, there we go. Hold on. Wait a sec. Voila. Okay, cool. Hi, everybody. 40 minutes, yeah? Okay. Cool. So I'm going to talk about Zama's FHE stuff and blockchain and how it all kind of goes together. So we'll do lots of introductions. If you don't know anything about FHE or anything, we're going to kind of give a little primer and then how it kind of used. Okay, so fully homomorphic encryption is basically you have a client and you have a server. The client encrypts some data, sends it to the server computes some program and sends it back. Kind of was originally introduced as like a client-server model where you could outsource your computation to the server and the server would do the computation for you. That's not, okay, now you can hear me. Right. So that's the basic idea. So how does it all work? So the idea is we use this thing called learning with errors. And learning with errors is basically if I have some secret key S, which is a vector, which is in like column version, and then I have an A and a B, which are public, and I multiply the secret vector by A, and I add a bit of eon, a bit of noise, then it should be hard to work out what S is given A and B. Okay? In particular, it should also be hard to work out that A and B has been generated in this way. So that's the learning with errors problem, and that's how we're actually going to generate our FHE ciphertext. So the search thing is can you find the S, and the decision thing is can you even tell it was come from such a computation. Okay, so how do we think about this? So what we do is that we do the learning with errors thing. We have the A and the B, but instead of just adding the eon, we add a shifted version of the message. If the E is small, it's an error, red, and the message has been shifted up, so this error is kind of lower than where the message is. So if we keep the error small, the message is still in there, and you can see you could decrypt by. If you knew the secret, you could take this value B, subtract the inner product of A and S. This will give you the shifted version of M plus E. E you could ignore, and you just get the message back. Okay, so that's basically learning with errors, ciphertext. So if we think about this, if to give you some idea, the dimensions of these vectors A and S are about 900. We're working mod 2 to the 64, and this plain text space here is somewhere between 2 and 10 bits of precision. So you can hold small messages, which is kind of, okay. Not big messages, small messages, but we'll see that that's not really a problem. Now, if we did this, if we have two messages encrypted in this way, we've got this error here and an error here, and if we just add the ciphertext together, if we add the messages, the sort of the delta M plus E bit together, the messages add, as long as it doesn't overflow this bit, and the errors add. Okay, so that's kind of, we could do homomorphic addition in some sense. The message increases and the error increases. Okay, the problem occurs if we've got too much error and we add the errors together, then the error will start mixing with our message and we'll get a wrong value. Okay, so we want to avoid this situation. We want to keep this situation where we've got a bit of gap between the error and the message, because if we don't, then we overflow. Okay? So we need some form of noise management technique. And that's where bootstrapping comes in. So what bootstrapping does is it takes a message with some noise, does this thing called PBS. We'll explain why it's programmable bootstrapping in a minute. So what it does is it kind of takes the message and the ciphertext, the input ciphertext, the SA and B, gives us another A and B out, such that the error has been decreased. You have the same message, but the error has been decreased. So that gives us a way of managing this noise, so we never get this issue of the two noises interacting when we add. Okay, so that's kind of So far, so good. It's all kind of a bit, looks actually how you do this is complicated, but from a high level, this is actually quite easy to see what you're going on. If you treat this as a black box, it's easy to see what's going on. Okay. Now, the point is that if we use this scheme called TFHE, so let's talk back. So this is true of any homomorphic encryption scheme. You can do this. The problem is that for many homomorphic encryption schemes, executing this operation here could take many seconds or even minutes for some schemes, yeah? But TFHE is very specific because it's very low latency for doing this PBS operation. Less than 10 milliseconds for 4 bits. We'll give some more for 4-bit messages, okay? So this means that we can evaluate this PBS operation super fast, and at the same time, we can apply any nonlinear function, like a table lookup. So the PBS operation doesn't just allow us to control noise, but we can evaluate any function we want at the same time as doing the PBS operation. Any function. So if you had a 4-bit message here, you can produce any of the 2 to 4 different functions you could get here. Yeah? So what does this mean? We have small messages, but how do we make it work on integers? Well, so the way to do that is that we split the integer up into, well, if you split it on a normal computer, you split it up into bits, but we can split it up into 2 bits. Why do we do 2 bits? We'll see that in a minute, right? So I take my integer, which is a U64, unsigned 64-bit integer. I split it into 32 chunks, each of 2 bits each, okay? And now I encrypt them, and I'll get something that looks like this. So I get 32 ciphertexts corresponding to my 64-bit integer. Okay, that's the first step. So that's how I'm going to do encryption of 64-bit integers. Okay, it's okay. No, I'll explain the next bit verbally. I thought I had another slide. So what this means is, because we've got 4 bits of space here, we've got 5, but ignore this top bit. You always have to keep that clear. So this means I can add integers together quite easily and still control this. And then I can do the PBS to do all the overflow management I want. Alternatively, I can multiply. If I wanted to do a function of M1 and M2, I could shift M2 up by 2 bits, add it onto this one, and then apply the nonlinear PBS operation on the 4-bit message, which is M2 concatenated with M1. So the fact I've got 2 bits, I've got 2-bit messages and 2 bits of space means that I can do all sorts of not only linear operations on each pair of bits, but I could also easily do nonlinear operations on pairs of bits, on 4 bits at a time. So that's why we kind of do this. You have 2 plus 2, so then you can do the shift to do the nonlinear operations. Okay, so that's basically TFHE. So TFHE is fast, and it allows us to do this nonlinear operations very quickly and control noise, unlike other FHE schemes. So that's component 1. And so this is what Zama's done. So what we have is this is in a library, TFHERS, which you can just use Rust. You can manipulate Rust. If you want a uint64 and you encrypt it, you get an encrypted uint64. So it's all very, very simple. There's also a sort of Python version, which is concrete. And then on top of that, there's an ML library to do Python style, PyTorch style ML. And on top of the Rust library, there's a blockchain application. And in this talk, I'm going to be concentrating on the blockchain application. And then underneath these things, you can plug in various things. You can plug in a CPU, a GPU to do efficient computations, or even dedicated hardware. There's a number of companies who are now producing dedicated hardware to work with TFHERS and all sorts of other libraries. Okay, so there's a bit of a stack you can kind of plug in at the bottom. Okay, so this is what we're going to be applying here. And then the rest of the talk is kind of looking at how's we going to kind of expand this and how do we make it threshold FHE. So here what we want to do is, the problem with FHE is that you've got a secret key, and the only person who can decrypt is the person with the secret key. So that's one problem. The other problem is the person with the secret key can decrypt. So he can access all the information. And what we want to do is stop having one person being able to decrypt anything at all. So we're going to distribute the secret key and then use some form of threshold MPC style system to do the decryption. Okay. So we're going to kind of look at threshold-friendly FHE now. Okay, so how are we going to do a setup? So we're going to have some sort of client. He's going to do a setup. And then we've got the server who's kind of also got lots of threads, etc. Okay, so we're kind of, think of a client is like a U and the server is a big, hunky server. So we've got to do various different tricks to make things efficient, because we've got the client here is kind of bounded and the server's like very powerful. Okay. So the first thing to do is, how do we do public key encryption? Now, the traditional way, if you read the literature, is to say, okay, so to do LWE public key encryption, what we need to do is create many encryptions of zeros. And then I'm going to, when I want to create a ciphertext, I take my message M0 and I just then do many encryptions of 0 and add them onto it. The trouble is these parameters are huge. To make this efficient, you need like 130,000 encryptions of zeros, which is like gigabytes of information. So for public key encryption, if we look at the literature, we need gigabytes of data just to encrypt one bit. Okay, this is clearly nuts. So what we have is that we've come up with a more efficient way of having using a kind of ring LWE-based encryption method, where we just have to give one encryption of 0, allows us to do many encryptions. So this reduces the public key size from gigabytes down to a few kilobytes. Okay, so there's some kind of, we've got to kind of make this as an efficiency improvement to start with. The next thing is this error distribution. Now, what happens is that in the literature, everyone says, well, the error distribution has to follow a discrete Gaussian. Okay? And that turns out to be, that's good for theory, but it's only really used in theory to show that there's worst case to average case reductions. In practice, you don't actually need the Gaussian distribution to be secure. So what we do is we replace this error distribution with something that's very close to a uniform distribution. And the reason for doing that is this means that we can do threshold key generation more efficient. If we wanted a threshold protocol to produce Gaussian distributions, that's really complicated. Whereas if we had a threshold protocol to produce a uniform distribution, that's easier. The reason why it's a tweaked uniform is because it's still hard to produce uniform distributions in MPC, but we can do something very close to a uniform distribution very easily. So that's so we have to kind of tweak we've tweaked the encryption scheme to make the public keys smaller, and we've tweaked the error distribution to make it easier to generate in a threshold manner. Then we've also got a problem, is if I'm in a public key setting, you can't assume the person encrypting the data is honest. Okay? The person encrypting the data might want to screw over the computation. So I could be encrypting something, you could be encrypting something, you could be encrypting something. You're the bastard. So what you do is you encrypt some bad stuff, and it then screws over our computation. You could actually encrypt something which already had the error being huge, which means that our computation would be wrong, or might be wrong a certain amount of the time, depending on what data we actually encrypted. So you would actually find out whether there was if you found out whether there was an error or not, that actually reveals information about our information. So what we really want is we want all encryptions to be good, to actually have this gap between the error and the message. And so what happens is when we do the encryption, we have to provide a zero-knowledge proof that the encryption has been done correctly. Okay? So that's another thing we have to add in. So we've got It seems to be, we've taken basic FHE and we've had to make the public key smaller. We've had to change the error distributions. Now we've had to add the zero knowledge proof in. Okay, so we've got all those. Oh my God, now we've got other problems. If you look at usual academic literature, it says, okay, for FHE, you've got to have, it's got to be in CPA. Okay, which means that the failure probability is, by here I mean the failure probability is the probability that your computation fails is about 2 to the minus 64. Okay, now that is equivalent, that's kind of close to the probability that a computation fails in the real world because something goes wrong with your computer. Yeah, if you do 2 to the 64 operations on a computer, it's likely that something goes wrong with the electronics. Some meson comes from the outer space and tweaks a bit on your RAM or something like that, yeah? So that's what normal academic literature talks about. But there's actually attacks against FHE, which happen in the kind of environment where we've got a threshold FHE, we've got threshold decryption, is that we have to worry about what's called in-CPAD attacks. And here to get 2 to the 128 security, we actually have to make the p-fail, the probability that we get a failure during the computation also down to 2 to the minus 128, which means we need much more clever ways of managing the noise such that we can still get efficiency, get to the 10 millisecond bootstrapping that we had earlier. So we've got to worry about this. Turns out, after I made these slides, there's what's called S in CPAD security, strong in CPAD security, which means we have to do even more complex things. But they're all done. We all do those. But it's a lot more complicated than this slide would from. So we've got to add all those things together. So what's happened over time is in terms of performance, we look at a 64-bit addition is in black, and a 64-bit multiplication. So in 2022, that's only 3 years ago, or 4 years ago, kind of soon, these times were over, these are in milliseconds, so over a second to compute a 64-bit addition or multiplication. And now we could do those we could do it in 10 milliseconds to do the 64-bit addition, and 61 milliseconds to do the 64-bit multiplication. So this is not just do the one PBS, but to do a full 64-bit addition is now there. So this is now, over time, it's got super fast, and we expect this is going to get even faster once we add in custom-based silicon. It's going to go much, much faster. Okay, so what do I want to say with this? Yeah, so, yes. So when I encrypt something, if I got 4 bits of plain text, I could actually encrypt it in this A, which is this very big dimensional thing, as 64 bits. So it seems that each ciphertext needs to be super, super fast, okay? But super, super large, which is a problem in practice, especially if I want to encrypt this and put it on the blockchain, which is a bit of a problem. If I had 32,000 bits just to encrypt 1 bit. So it turns out I can actually do a form of compression. So we can compress the encryption down so for a 64-bit integer, we can actually get it down to 527 kilobytes as well. So we can, that's kind of, compression only takes 5 milliseconds, decompression takes 18 milliseconds, so we can compress and decompress very efficiently. So this reduces our size down as well. Okay, so we've now got all those things together. We now actually have to look at secure threshold decryption. So here, we've got a problem. We have to do this thing called noise flooding. So this is what a standard ciphertext looks like. It's got a big bit of noise, a small bit of space, and a bunch of message. But when we want to do noise flooding, to do threshold decryption, we've got to have a big amount of space here. Okay. So what we do is we do what's called a big PBS, so to enlarge the queue. So instead of thinking of the PBS operation as something which squashes the noise, what we're now going to do is we do a PBS operation which keeps the noise about the same size, but increases the queue. Okay? It's kind of like doing it think of it in a different way. And then this gives us a big gap here, which allows us to do noise flooding to get threshold decryption. So this. So what I kind of want to say from those all last slides is that we have something that looks very simple, just going, we're going to do TFHE, it just does LWE, but actually to make it usable in practice, we've got to add all sorts of bits and bobs on to actually make it really usable. We've got to make the ciphertext smaller, we've got to worry about real security, etc., 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 and we have to worry about this noise flooding. So we have to have, it's got to be bandwidth efficient, we've got to get the ciphertext smaller, it's got to be storage efficient, we've got to have MPC-friendly key generation by making that the uniform distribution instead of the Gaussian distribution, and we've got to make it in CPAD secure. That's a kind of a summary of what we've just had. Okay, so how do you all use this? So this is a bit of TFHERS code just to show you how easy it is. So if I have a U8 and a 27, A is a 27-bit value encoded as a unsigned 8-bit integer, 128 is a unsigned 8-bit integer. I just encrypt them. This is what would happen on the client. On the server, I could then do A plus B, which this is encrypted, and then if it came back, I could do the decryption. So you can see it's quite easy to write a program which does operations on 8-bit integers or 64-bit integers or whatever. So that's kind of nice and simple. It's open source, it's in Rust, and as you can see from there, it's super, super easy, user-friendly. The API is very much a la Rust. There's everything to do with homomorphic arithmetic. You can do additions and multiplications and all sorts of other interesting stuff on the integers, on the encrypted integers. There's crypto parameters already built in and lots of cryptographic primitives for you to play with. So we got that. Also in the library is all the zero-knowledge proofs you need to do to do the encryption. Like I said, you have to add a zero-knowledge proof in. And the ciphertext compression and everything else I've talked about. So that's all within the library. And you can download it on the GitHub. And there's a huge kind of handbook that explains how to use it with various bits of code and whatever. Okay. So what's coming up? We're going to improve performance, but the main thing is actually producing a stable GPU backend. For GPUs, we get a large performance. So why do we get a GPU? Why do we get a performance improvement with GPUs? So it turns out that the main computational cost is doing this PBS operation. And the PBS operation is essentially doing FFTs or NTT operations. And that's essentially a linear operation. GPUs are very, very good at linear operations, matrix multiplications. So if we use GPUs, we get improved performance. To give you some runtimes, going back to that graph. So we had the addition. So on the CPU, it's 100 milliseconds to do an additional subtraction. GPU, it goes down to about 9.9. We can do bitwise operations, you can see. Division is always a pain, as it is always in computing. Division is always a pain. Okay, so that's the FHE thing. And kind of some tweaks to get some threshold stuff. I think Phoenix are giving a talk later. They're going to talk about threshold decryption a bit more. Yeah. So I'll leave all the bells and whistles to you. Okay. So as I said, in Zama, what they've done is they've kind of used it for building what we call an FHEVM, a fully homomorphic Ethereum virtual machine. And why the hell would you want to do that? Well, so this is a ledger. And as you can see, everything's public. So it turns out this is absolutely useless. Right? Blockchain is absolutely useless, really, because no one, if you want to, if you're using this in any form of real finance, no one wants the values encrypted, or so we've got to actually add encryption onto this, because otherwise it's not going to take off. Just a bunch of blockchain geeks using it isn't really mass adoption. I know they might think it's mass adoption, but it isn't. It's not your granny using it, or everyone using it for all their finance. Yeah, no one wants to see. Well, maybe you do want to see how much I'm paid, but I don't know. But I would like it that you didn't see how much I'm paid, yeah? So it's kind of, so there we go. So we want to stop, if criminals know what you own, they can easily target you. So actually in France, there's been kidnappings of people to try and extort people who the criminals knew had large crypto holdings. So people were kidnapped and ransomed if they didn't hand over all their Bitcoin or whatever. There's surveillance. You could be surveilled, not just by government, but anybody. And there's also MEV, so bots front run you because they know what you're doing. So we want to avoid these things. So there's many privacy issues that the fact that everything's public is a problem. So you could do, there's various technologies that allow you to keep things private. We have FHE, Zero Knowledge, and MPC. MPC is kind of very decentralized. That's kind of nice. FHE and ZK are not really very decentralized at all, unless you have a threshold version of FHE. MPC and FHE are composable, and by this what we mean is that if you do ZK stuff, the person producing the zero knowledge proof has to know all the information. So they're producing the zero knowledge proof. So the person producing the zero knowledge proof has to know all the secret information. And it seems very hard how to actually kind of compose, I'm sending money to you and then you're sending money to this person. Then you have to know something. And it's really, how do you actually do the ZK to actually make this work? Seems really complex. But the advantage of ZK and FHE is that it's non-interactive. So we kind of have, there's pros and cons for all approach. And kind of we've gone for the FHE approach but addressing this missing gap by using threshold FHE is the point. Yeah. So we could do confidential smart contracts. Basically, you encrypt. It's when you add something to a blockchain, you encrypt the data. The data's on chain, and everything's compatible. So this doesn't create a new L1 or a new L2. This runs directly on Ethereum straight away. Yeah, it doesn't. You just write your stuff. It just runs on Ethereum, and then something magic happens in the background to make sure everything's encrypted. The computation's done on Ethereum, and users still know what contracts are doing, and they're easy to read, the contracts. You can implement your own access control logic, and they're composable. You can mix data from multiple users and compose one smart contract with another. So how does the architecture work? So you've got the host chain. That's like Ethereum. So just imagine this works as normal. And what this does is when you access variables in the smart contract, you're basically just accessing pointers. So it's basically saying, if I want to add 2 encrypted values in the smart contract, I'm just saying, okay, I take encrypted value A, which I don't, I take it, but I don't. So I just kind of virtually take it. I take encrypted value B, and then I produce the encrypted answer C, but I just go, C is going to be the addition of A and B, and I'm just saying that the pointer C will point to something which will be the encryption of A and B. So that's what the actual smart contract actually does. Then what happens in the background, the magic is a bunch of co-processors actually go, oh, on the blockchain, someone wanted to do C equals A plus B. So the co-processor will actually execute the homomorphic addition and it will maintain the database of here's the pointer and here's the ciphertext in some sense, okay? And the reason for doing this is because this means Ethereum doesn't have to do the homomorphic addition, which means you don't have gas costs. Yeah, don't have high gas costs because. So this pushes the actual computation to the co-processors. There's a gateway which coordinates the co-processor and other things, and there's a key management server which holds the key for doing decryptions. So at some point, I want to know how much money you've transferred me money. I want to know how much money you've transferred me. So what I do is I can decrypt my balance and see what it is. Yeah. So I need to have some access to some secret key, but I'm going to mitigate that access to the secret key via the smart contracts on the host chain, the gateway protocol, and this KMS working together. Okay, so here's a user. The user talks with the host chain just like they normally would, And if they want to do something special, they interact with the gateway. And the gateway looks at this database that the co-processors compute and an MPC thing over here, which does distributed decryption and key generation. Now, here there's kind of two bits of MPC going along. There's MPC here, which is like traditional MPC, in the sense that it's MPC. So it's like an MPC program. It's traditional MPC. But we have replication on the co-processors, because this allows it. So we also get we want to check that these guys are doing the correct result as well. So what we do is we have that the co-processors basically, because all the executions are deterministic within FHE, they can all compute they all compute the same thing, and therefore you can check that they've all computed the right thing, because if there's at least an honest majority here, they will all compute, those honest majority will compute the same thing. So you can check, oh, you've computed the same thing, you've computed the same thing, you haven't, you're the liar. Yeah? So there's a sort of simple MPC replication here, but a more complex traditional MPC thing going on here. So this allows us to unlock new cases. You could do, we can manage the swap tokens without actually anyone else seeing the values. We can execute blind auctions. Okay, so the traditional thing in MPC is to talk about the sugar beet auction from 20 years ago, but you can now do auctions on chain where no one can see the values quite easily. You could do games, you could do poker, blackjack, encrypt cards or whatever. You could do encrypted IDs and private transfers. So there's all sorts of use cases this unlocks. So I'm going to go a bit deeper down into the architecture. So what you can see is that this is actually just more complicated than just doing FHE. You do FHE, but we've had to add MPC on to be able to do threshold decryption. And we've also had to add zero knowledge on. So that table I had earlier, which I said, okay, you could choose between FHE, MPC, and zero knowledge, is actually a bit of a lie. You actually have to use them all together. Yeah, so that's a kind of different. Okay, so let's look at a picture. So here we have, so the blockchain is going to have some public key, which everyone agrees on, and this has proof of stake consensus. And then the KMS is going to have a secret key, which shares the secret key out between the KMS servers. So we kind of think of it as two things: a proof of stake consensus network here and a KMS network over here. And essentially, the system is how these two things interact. So the first thing we need to do is we have to run a threshold key generation. So we start with nothing. Let's think of 2 or 3 or 4 or whatever, how many servers. And they're going to do a threshold key generation. So they execute a big MPC protocol to generate shares of secret key and a public key here. Then that one public key gets certified and passed over to the blockchain, so every entity on the blockchain has the public key. So that's the kind of setup process. And then everybody on the blockchain could encrypt. This guy could encrypt some value. This lady over here could encrypt some value. They put them on the blockchain, and then we could just get the encryption of Z by encrypting the two values. So this all, like I said, this is kind of happens on Ethereum, on the pointers, and then on the co-processors, this happens in real life. And then we've got this encryption, and we want to decrypt it. So what happens is that the encryption comes in here. This person, the KMS has a shares of the secret key, and then it executes another MPC protocol to give the actual X. So if you wanted to know your balance, you would execute a smart contract which said, give me my balance. This would go through the logic. It is your balance. You are allowed to decrypt this value because it does correspond to you, and then it gives you the value back. Okay. So if you want to send it back to a user, what they would do is they'd decrypt it, encrypt the value back to the user, and it would go back to the user. The key point is only the user with the secret key corresponding to this public key can know the value. So if you did ask for your balance, only you get it. So that's how it would work. Okay. So I showed you the programming the Rust. If you wanted to use the Rust API, is easy, but clearly you can't use Rust on Ethereum. So the Solidity API is just as simple. Okay, here's a Solidity program, which you probably can't see at the back. But here we go. This is a transfer. I take the encrypted amount. I take it where it is. There's got the zero knowledge proof attached there. If I want to do the transfer, I have to work out is there enough money in the amount to transfer. If there is, I've got this encrypted Boolean, and then I just do the transfer with kind of like a mux. So it's kind of really, so the values are really simple. The API is very, very simple, very easy to use. So here we have, this is a mapping from the address to the encrypted balance. This is why the address is basically these pointers I've been talking about. And then there's all the different types that you want, plus all the different operations that you might want to do, arithmetic operations. So in particular, there is no modification to the Solidity compiler. Hold on, go back, hold on. Yeah, there's no modifications to the Solidity compiler, and you can use it with all sorts of other data types. It's kind of nice. Yeah, so the key point here is this zero knowledge proof that you've got to check, that it's got to be checked, but that's actually done using this operation from external, just checks the zero knowledge proof that you've attached to the encryption. So if you encrypt a value, you have to check the zero knowledge proof, but that's all done for you when you load it into your smart contract. Okay. Yeah, and then Crest decryption, that's kind of easy. Yeah, okay. So it's currently working with Solidity. We're going to expand it to other WASMs and other VMs in the coming through. So what happens inside? It's a bit more of a picture. We've got the host chain is here. We've got as is replicated as usual Ethereum. The events get monitored by the coprocessor to add. And then there's this Oracle thing which transacts with the gateway to the KMS to get the events. So if you want to kind of decrypt, you make a call to the Oracle. Sorry, you make a say here, I want to call the Oracle, goes back to the gateway, KMS gets the value back to the user. Or it might be you want to decrypt the value and put it back on chain, in which case you decrypt the value and it goes back via the Oracle to be put on chain. The coprocessor itself is as a listener, the database and compute workers. So there's many of these who are listening to the chain to see what they should compute. But the database will be identical on every coprocessor, which is the main thing. And then finally, we're going to look at the KMS backend. So we have these parties. This works with different MPC parties, and they're going to they just interact themselves. But this is kind of hidden from the user. This is run by current plan is 13 very highly trusted organizations are going to be running this MPC protocol. So think of N is 13. So the overview of this is that for those of you who know MPC, there's some tweaks we have to do. So we're going to do secret sharing over rings. So normally MPC has done secret sharing over finite fields, and we can't do that because we've got arithmetic modulo 2 to the 64. Okay, so that's a bit of a problem. We need the MPC also to be robust. So what do we mean by robust? So robust in MPC land means guaranteed output delivery. So if I ask you to, so if I've got a bunch of people over here, there are my MPC servers, and I ask you to decrypt, and one of you's offline, I'm stuffed in some MPC protocols. It might be that one of you's online but decides to be devious, in which case I'm stuffed in some MPC protocols. So it must be that even if a certain threshold of the parties are either offline or lying, I can get my value back. Yeah, I don't want everything to halt just because one of the KMS parties is either misbehaving or being bad. So if we have 13 MPC parties, we can actually tolerate up to 4 of them being either offline or bad. Okay. The other thing we need is, in terms of performance, is we need the protocol to work over asynchronous networks, because the internet is not synchronous, despite theoreticians and cryptographers thinking it's synchronous. It's actually an asynchronous network. So we need the protocol to run in an asynchronous manner, which means that we can't just rely on, the kind of MPC that you get in, academic prototypes like MP speeds or things like that. Okay, so we have to do rather complicated MPC to start with. Okay, so this is fully actively secure, robust MPC over Galois rings and asynchronous networks. Okay, so there's one. We have to do this switch of squash, which is moving this go from Q to 2 to 64 up to 2 to the 128. So we have to have this special thing to make gaps for the the noise to go in. We have a noise flooding technique for the MPC protocol, which is so traditional noise flooding is you just add on one bit of noise and then you say I'm fine. Turns out that that's not really good enough in practice, and so what we do is we actually add on 2 pieces of noise, which sounds kind of weird. So if you have one bit of noise which is uniformly random and you add it in, you kind of, so so why do I add in noise? So imagine I've got a 3-bit well, let's go do maths easier, a 2-bit integer, and I want to make sure that you don't know what the 2-bit is. So what I do is I add on a random 128-bit integer. And the point is if I add on a 128-bit integer and then reveal the value. So if I ask you to decrypt a 2-bit integer, you know what the value is, yeah? But we don't want you to know what the value is. So what I do is I add on a 128-bit integer, and this gives me a 126-bit integer. But the probability that you can work out what the original 2-bit integer was given the 126-bit integer is really small, because that's about adding, that's to do with the bit propagation. So if I started with a 2-bit integer, the maximum could be 3, then the probability that I get the top bit of the 126-bit integer is equal to 1. In other words, you started with a 3-bit integer, is 2 to the minus 128. Yeah, because the probability that if I add on a 128-bit integer to the number 3, the probability that I get a top bit is 2 to the minus 128. Okay, so it turns out, but that would be a problem, because to get 2 to the 128 security, I have to add on a 2 to the 128-bit random number. However, if I add on 2 random numbers rather than 1 random number, it turns out that if I add on, say, 2 64-bit integers to my 3-bit integer, the probability that I actually get the top bit of the 2 to being 2 to the 2 to 64, 2 lots of 64, like the 65th bit into the 65th bit, the probability the 65th bit is set to 1 is actually also 2 to the minus 128. So by adding on 2 random numbers, it's actually more efficient than writing on one single big random number, which is kind of a bit weird. But so what? It's not flat. Okay. Yeah. So we have to do that. Well, we've got fully simulation-based security proofs, which you can look up if you look up Noah's Ark on ePrint, you'll get the paper. And the performance is less than 500 milliseconds for 40 parties on a WAN. Turns out that basically, if you kind of think of this as offline pre-processing, which in our system, we kind of think of this as offline pre-processing, that this could be, we could ignore this in terms of the latency for the user of requesting a decryption. This has already been done. So this is kind of done in the background before the user. So when I actually request, it actually goes down to a few tens of milliseconds delay for actually requesting the values. So yeah, if you treat this as offline, we can actually get this down to tens of milliseconds. And that's basically one ping time between the servers. So if your servers are all in the same continent, and your ping time's like 10 milliseconds, then you'll be fine. If you've got servers distributed across the world, your ping time's probably about 100 milliseconds, and so you would get 100 millisecond latency. So your latency, taking this as the offline taking this as offline, the actual performance cost, the delay for the user is actually the ping time between your KMS servers, which is at most 100 milliseconds usually. So there we go, and I've got a few minutes left for questions. Sorry for the massively fast thing, but as you can see, loads of stuff to cover, and there we go. There's one over there.
In a real-world financial use case, right, apart from just the balances and the Ethereum addresses, there are more fields that would need encryption and privacy on. So would homomorphic encryption or TFHE would address those?
Yes, you can modify it to do that. So at the moment, this is just purely demonstrating just on the balances. If you want to do like the from and the to field, which is the obvious next ones to do, you could encrypt them. There's some interesting tricks you could do there to make that more efficient, but from which we'll go to on another time. But just at this moment, yeah, you would have to do extra, but they're easy to do. But you just do some extra tricks, yeah.
So it is a scalable solution.
It does scale, yeah. It scales to the other ones. If you do it naively, it doesn't scale on the from and the to field, yeah, because you can kind of go, okay, I can do silly. I want to encrypt. The stupid way of doing it is I want to send to you, so I encrypt you, and then somehow I've got to go through all the users on the planet and work out which one's you that I've encrypted, and then add to your balance in a way that's I'm not adding to everybody else's balance. And then to do that, it's quite hard because if I only add to your balance and I don't add to your balance, then I know it's not you, so it must be you. Yeah. So doing it naively is silly, but there are ways of doing it cleverly which you can solve that problem. Yeah.
Thank you.
That is a good question. So I think part of the problem here is that there's trade-offs in any system, yeah? And so what happens is that you can think of trade-offs as availability, time, and your level of distribution of trust, yeah? So a traditional blockchain goes, okay, we're going to really ramp up the distribution of trust to absolutely maximum possible, yeah? And that's fine, but the normal blockchain does not actually hold any secrets in some sense, yeah? So it's ramped it up to maximum because it doesn't have to distribute secrets. We have to distribute secrets. So on the KMS side, if you have a secret that you're distributing, you have to bring that level of distribution down, the trust down, okay. Now, that doesn't normally hold for threshold signatures, which are used on blockchain. And the reason for threshold signatures is usually I'm distributing the secret key as via a threshold signature scheme, my own secret key for a threshold signature scheme. So it's my trust, my key. Whereas this is a master key that everybody has to trust. So there's it's somewhere between normal threshold signatures in terms of distribution and blockchain, which is maximum. So, so there's this gradation. So I'll come back to the co-processor. So purely on the KMS side, you've got to have something in between. Okay, because it's impossible to be maximum, and you don't want the threshold signature level of we're only going to trust 3 people. Okay. Now the reason why in the threshold signatures you can trust 3 people is because if something goes down, it's one of your servers has gone down, and therefore, haha, I can't sign this thing. I now have to reboot one of these things. Whereas here what we have is we have something where if 1 or 2 servers go down or act maliciously, I still don't want everybody to be impacted. So that's why it's not 3, it's 13, and why the threshold is n over 3 rather than n over 2. So this is purely, it's a function of the math and the fact you have the secret key. So there is no way around this, okay? So because there's no way around it, how do we actually get the confidence that things work? So that, or the confidence for the users that you can trust them. So this is the same argument would apply for the KMS as for the co-processors. So the entities that are chosen to run this have to stake a large amount of value. So if they go wrong, everyone else knows they go wrong. For the co-processors, it's easy to see they went wrong. You and you computed, you did something different, you get slashed, yeah? And in addition, for the MPC parties, they know when someone else lied when they're executing the protocol. So if a majority of them say, you lied, we know you lied. So there's staking. So there's 2. There's 2. 1, there's staking. And 2, they're organizations which also, they're not just anyone. These are people who are organizations which have a lot of other trust and manage a lot of other assets on behalf of people in the community. And so if they're slashed, 1, they lose their stake, but 2, they lose their reputation, which is probably 20 or 30 or 100 times more than their actual stake is actually worth. Yeah? Yeah, I didn't say that there's staking. Yeah, okay. Yeah, so there's an economic argument that they do right, but they're not just anyone. And then to also, as an extra precaution, they all are operating their code is also in Nitro enclaves. So you get so in some sense that's also for their help, because they then know, okay, we know we're running the right code. We're not, so they want to do it correctly because they don't want to be slashed by mistake. Yeah. So, but that also acts as help for the rest of the community as well. Yeah, but this allows you to put, so your AML and KYC rules, it can integrate in the smart contracts. So this also can be used to solve the problem of the KYC and AML rules. So you're not allowed to, so you could actually put, if you've got rules and regulations, you can encode those within the smart contracts. You can encode that if you're in a certain jurisdiction and you're doing some transfer. So for example, if you're doing this in high finance, there's always got, whilst it's all secret, there's always got to be an escrow capability, because each trader is doing stuff, and if they do a fraud, they have to open their books to their manager to say, yeah, so that can be encoded in smart contracts that say, okay, if this jurisdiction, this person's trading, we can reveal the values. So you can encode all of the regulations within the smart contracts, which you can't do with Monero. Yeah, so I mean, it's actually to address the KYC and the AML, that this is why this is much more powerful, because you can do that all with the smart contracts. And then it's very clear that you can do this because the smart contract enables you to do whatever you need to do to reveal data or whatever, to keeping regulators happy. Yeah. Is there anyone else? Yeah.
Yeah, I have two questions, and apologies in advance because, well, I have absolutely no idea how FHE works.
Neither do I really. There we go. It's magic, yeah?
Sure. So the first one would be: are there any best practices or experiments that you have done on translating legacy applications to the setting where fully homomorphic encryption operates in? For example, if I have a complicated protocol that has, say, PyA in it, do I basically get rid of PyA and try to make it so that I use the FHE stuff, or just directly translate it?
Okay, so the first thing is you could just do it directly. Okay, you could just go, if you know, suppose you had, I mean, the classic application of PyA encryption is to do electronic voting. Okay, so that's that's the classic one. So you could use PyA with electronic voting, or you could even use Elgamal exponent with electronic voting, and you could just rip that out, just replace it with TFHE. However, that's not such a good idea. And we just put something on ePrint a few weeks ago, where we actually look at the electronic voting example, and by using some of the properties of TFHE, we actually get a voting protocol in some instances which is hundreds of times faster using TFHE style techniques than using traditional Palea techniques. So whilst you can just rip it out, the protocol, and replace it, that's often not the best thing, because people, if they're using Palea, they've engineered the problem to be suitable for Palea, and that engineering has actually made it really inefficient. Whereas if you just take a step back, you can make things go much, 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 much faster, because you've got this, if I just give you a screwdriver and tell you to service your car, you could probably do it, but it would take you an awful long time, because you'd to build the wrench, you'd have to use the screwdriver to make a thing, to build a wrench, to do this, to do that. Whereas if I said, here's a garage full of all these capabilities, service your car, it would go much faster.
Fair enough.
Yeah.
Fair enough. And my second question is, how much of the, well, I guess let me phrase it this way. Why do you model your network as asynchronous? Well, I understand that there are some n/3, n/4 limits there, and automatically you get robustness and whatnot. So you have some nice properties if you model it as asynchronous, because you could say you have no other choice. But if you are operating on the blockchain, which is itself not asynchronous, why would you model it as asynchronous?
So this is a really good question. So the point is some things are on the blockchain. Yeah, so look at this KMS backchain, a block thing, for example. Okay, so we're acting with the gateway, and the gateway is talking to the blockchain, which is on the left. Yeah, way on the left. Right. Now we want this to go fast. We want the KMS to be super fast. Now, what a blockchain actually does is, in some sense, it turns the asynchronous internet into a synchronous network. Because basically what you say is, I want to send a message to everybody asynchronously. So what I do is I write to the blockchain, and now everybody reads that message. And so what I've actually done is, in some sense, the blockchain has turned an asynchronous network into a synchronous one. Yeah? But the problem there is that the write to the blockchain takes long. Yeah? I have to write, I have to wait the block be confirmed, and then I have to wait and then bring it back. Yeah? Which takes time. Whereas if I've just got direct TCP connections, I'm actually running over an asynchronous network. So if I was running the MPC communications over a blockchain, that would be orders of magnitude slower than using the internet to do the communications. And if I'm using the internet to do communications, or internal connections within a data center, or very fast fiber optics between data centers, then I'm always in the asynchronous setting. So yeah, so it's kind of it's purely because of time. Yeah, you could write to the blockchain. I think there's some wallets. So some MPC wallets, they run an asynchronous protocol, and they use the blockchain as a way of creating the synchronous thing. I think, yeah, I read this once. Someone was doing that. But then with the wallet example, again, latency isn't an issue. Latency is the real issue here. It's not throughput, it's not an issue. The key is how long do you know, here I am, I haven't got the video like Abby had of here's my app connecting, yeah?
Yeah. I think it was Damgard's Secure blockchain
Yeah,
wallet
yeah,
thing
yeah,
that had
yeah.
like a
Yeah. So
thank you.
latency is really the killer here. Anyone else? Oh yeah, no. Yeah, keep going. Uh-huh. Yeah. You could do anything you want. The question is whether it's efficient. But what I would suggest is that the people who have used any form of FHE or MPC to do machine learning have actually looked at their application very carefully. And the way to think of, you can do image classification super fast in MPC and FHE. Encrypted image classification, super fast. There are deployed products which do this. And the trick is to engineer the application such that the amount of MPC or FHE is really tiny. And it turns out with image processing, you can do that. But you have to kind of, I will leave it and then you can think over the coffee break of how you would do this. This is a student question. How do I engineer? My application is, okay, so here's the application, answers on a postcard, because I know what the answer is, okay. I take an image with a mobile phone and I want the server to tell me whether that image contains a cat or a dog. And I want the server not to see the image. So how do I do that? And in fact, it might be that the server is actually saying whether it can, but even easier, the server is going to determine whether the image contains an X, and I don't know what the X is, but it will just say it does or it doesn't contain an X, and the server doesn't know what the image is. And it's actually really, really, really simple to do, really fast, and answers on a postcard after the coffee break. Thank you.
Thank you, Nigel. That was truly thought-provoking